Good morning, everyone. Thank you for attending my demo talk on leveraging CMSIS. We've done some ports of the DSP neural network as well as the real-time operating systems and NVIC API. Now, nod your heads up and down or left and right to if you agree with my assumptions or disagree. But my first assumption is the vast majority of projects begin with legacy code. I believe that is true, right? There's very few projects that you start with brand new code. My second assumption is for small embedded applications, the vast majority of those applications are based on code that's on a ARM Cortex. Do we agree or disagree on this? Oh, we got I like to have some disagreement, so that's just great. And so my third assumption is that for those applications, if I'm looking for DSP-based embedded applications, a lot of them are using the open source CMSIS library routines. They could be the DSP routines, neural network, RTX, for example. So those are the three assumptions that I'm going to go forward with this presentation. Now the question is, why do we port to RISC-V? Some people might say it's because it's not ARM, or it's an open standard, or that it's a more innovative architecture, but I don't think any of those are reasons that people port to RISC-V. The reason why people port to RISC-V is you can create value. That's why people port to a different architecture. Now, the definition of value by the Oxford language is something that is important, worth, or useful of something. That is the definition of value. So that could be, I got a smaller core, so it's less cost, so I can save money or make more profit. It's more efficient, so I save energy, or I can potentially do more. But I don't think that is really value. Value is only created when you can use those benefits to create something that has perceived value by others. Now, let's take a look at an example. Now, say if I'm a sensor company, and I have a sensor that I sell, then someone else puts an external microcontroller on that. And the thing is, the sensor might be a few, say 50 cents, and the microcontroller might be $1. I want to create more value by actually integrating that sensor with an intelligent AI-based microcontroller. Now I'm going to take those two ICs, one that someone else is getting the revenue from, one that I am, into a new device. This new device will bring value to my company because I have a new product that I can actually sell at a higher ASP and hopefully get into new business segments. So this is an example of creating value through RISC-V. Now, to extract value, we must have an application. And going back on the assumptions that value is, or that most of these embedded applications are based upon ARM and ARM CMSIS, we want to abstract the hardware or the core from the application. ARM does that already today using CMSIS. You can write a single application that runs on the M0 Plus, M4, M33, M7, M52, whatever the core is. And then the library actually will extract the most effective library for the particular core. So we're going to do the same thing, but now we're going to port to RISC-V. Excuse me for a second. I'm just going to close the door here. Sorry about that. It's a little distracting over here. So now this is actually how it works, right? You have the software application, and when you do the build of your application, you're saying I'm going to build to, say, maybe a ARM Cortex device or RISC-V, and then it chooses the proper library, and it links the proper library for you. So at Codasip, we've made our CMSIS libraries core aware. What that means is when you build your core, it actually looks at the core and figures out what is the optimal CMSIS library routines for that particular core. Now, when I actually did this project, the performance numbers on our core were so significant, I had to do a little research on why did we get such good numbers. And a lot of it came down to, I think RISC-V is a welcoming architecture for innovation. Now let's take a look at the M0, M4, and RL110 that we did in the study. Now, we have the different bus architectures. M0 has a single instruction data bus. Both M4 and L110 have a separate instruction data bus. The memory cycle time, this is where you get a lot of performance out of the RISC-V microarchitecture of the L110, which is single cycle, compared to the ARM, which is 2. But another key factor is when you look at the M0, its parallel multiplier is only a 32-bit result. Now, if you're doing Q31, which is used for higher precision, it is a fractional math. And when you do Q31 multiplies, the result is actually in the upper 32 bits. So for the M0, you actually have to do software emulation. So what does this actually mean when it gets to running your application? Now, first of all, if you use memory copy in this particular application, you did 2,000 words mem copy quite often. And when you take a look at that, by the more efficient architecture of the L110 and RISC-V, we're 3 times faster than the M0 and almost 2 times faster than the M4. Now, if you take a look at Q31, fixed point multiplies, we're 69 times faster than the M0, but we're at the same time as M4. So we're getting to understand a little bit about the architectural differences between the Cortex family and the R implementation on the L110. Now, what does that mean when you get to the next level? That's sort of the base instruction, but now let's take a look at a function. Now, at the functional level, what does that correspond to? Now, I'm looking at a complex FFT. Now, when I'm running the exact same program, because we're running CMSIS libraries, the exact same program on all these cores, and I'm running them on an ARM eval boards from STM32s and simulated R's on the L110, we can see that our L110 is running 10 times faster for FFT over M0, and approximately 75% faster than the M4. Significant improvement. We've also added custom instructions to have what I call, down on the bottom here, DSP extensions, which actually improve the performance further. Now, let's take a look at a FIR filter. So a FIR filter does a lot of multiplications and a lot of data movement. Now, when you look at that, our performance is even higher or even more impressive. We've also implemented an accelerator, a DSP accelerator, which actually provides, I think it's like 73 times faster than the M0, and compared to the M4, let's see, that's about 3.5 times faster than the M4. So we get in a lot of good performance out of this small core. Now, so we started on the architecture, how basic instructions, the performance between the different architectures, and then on the functions. Now, what does it look like in an application? Now, this is based upon a stereo application in a relatively high performance or high quality. And so we're going to take a look at how the buildup of all these benefits of the RISC-V architecture are providing value. Now, if I calculate the number of cycles for the M0 to do that application, I would need to have an 800 megahertz M0. So I don't think the M0 is actually possible for this application. Now, let's take a closer look at the ones on the bottom. Now, we're looking here is what's the frequency required by the different cores to do this stereo application. Now, our core that's not modified with any DSP extensions requires the same frequency of performance as the M4 or M33. But our ones with the DSP extensions or accelerators are actually require less, a lower frequency. Therefore, you can actually save energy, lower power. Now, but what happens if area is more important? Now, you can take a look at it, that the area for the ARM devices are off their website. And so you can see that our base core, which requires the same frequency as the M4 or the M33, is roughly 1/4 the size. So a significant area savings. Even our higher performing devices that have the DSP extensions are smaller than the comparable ARM devices. Now the question is, I believe the true value is here with RISC-V, right? We've proven that we can get higher performance out of the RISC-V architecture, as well as higher performance with RISC-V architecture. It's more efficient and it's lower area for cost. Now the question is, second and third order of value, what are you going to do with all that additional performance? Now you can start thinking of new applications that weren't possible before, or new battery applications because we are much more energy efficient that weren't viable before, or some combination of that. So I'm basically saying that legacy software, as a hardware engineer, I used to not like legacy software because I always thought it prevented processor innovation. But now I'm saying that legacy software is no longer an obstacle to processor innovation, but it is actually a driver of solution innovation. Now, if you come by our booth, which we're on the top level there, you can see a demonstration where we're taking a MATLAB application that we developed all the way from MATLAB to CMSIS to running on our core, and we run that same application on our core and the different ARM cores, and you can see the performance benefits. But legacy software is no longer an obstacle, and if you are available or if you're interested, I also have a email alias where you can actually send, and I'll actually run your application, your CMSIS application on our core and on the ARM cores, and give you a report back so you can see the value you get from RISC-V. So thank you very much, everyone.